Is it zoomed into about like the board?
Yeah.
Okay, cool. I will begin. Holy Father, we thank you for this day. Again, Lord, I thank you for these students. Pray you bless this class, Lord. In your name I pray. Amen. Actually, it reminds me, I reset the mic in the last class, and I'm probably deafening people right now because I had somebody wasn't wearing it. They were. There we go. There, that's more reasonable. All right, so I posted, recommended homework, and I've already shown you guys how to solve a good bit of that, but not all of it. Before I forget, let me give you back your homework. So you guys, so hand that back to John, Brian, Alexandra, Jeffrey, Tamara. Oh, there's two there. Hiram, Abigail, Joshua, Grant, no Grant, Nathaniel, Prince, and Brandon. No Brandon. All right. Well, I'm just giving them back to you because I didn't give them to the grader. The grader I don't think has time at this point. So I will assume that all of you did better than, anyway, it will appear in the grade book. You will not be bothered by it. At least that, yes. All right, so don't tell me these sorts of things. It's a Christmas miracle. Let's see here. All right, so where was I? Yes, I've shown you how to solve many of the problems that I recommended, but there's just a sort of, I've spent some time delving into applications, but the application I'm most interested that you learn is just sort of the basic geometric application of differential equations. And so let me just try to expand on that theme here for about 10 minutes. And so the idea is really simple. I'll start with a really basic example. Suppose I want to find a family of curves which has constant slope m. So what does that mean? That means I want to have dy dx equal to what? M. And so how do you solve this? Well, I'll separate variables just to be, dy is m dx, right? Integrate both sides, what we got? mx plus a constant, right? Of course, this is not surprising. You guys knew before I said anything about differential equations that a family of curves with constant slope are lines with that same slope, right? So let's bump it up a notch. Suppose you want to find curves whose slope matches the y value at each point. So what would that say? What the slope is dy dx, right? We want dy dx equal to what? Right, so we're trying to solve dy dx equals to y. So we do that. What do we get? We get dy over y equals to dx. We integrate both sides, what do we get? Natural log the absolute value of y equals to x plus a constant. Then we exponentiate both sides. What happens? But by laws of exponents, that's e to the x times e to the c. And so here we are back again. Y is equal to plus or minus e to the c times e to the x. Mathematically, I did this yesterday. Different letters, but same story, right? So you could say y equals to, say, k e to the x. So the exponential function, or any constant multiple of the exponential function, is such that its value is equal to its slope at each point. And you could say, if you wanted, you could define the exponential function using this, right? You could say, definition, e to the x is the function such that example 2 holds, right? And what else? Say f of x equal to e to the x is, and then such that also we also need f of 0 is what? To make it e to the x, we need what? 1, yeah. And you could use that as a definition for the exponential if you wanted. All right. Let's try to do a little bit something more interesting. Suppose you want a family of curves, all right, which is increasing before x equals to 2, but it's decreasing after x equals to 2. With two things. One, increasing whenever x is less than 2, and 2, decreasing whenever x is greater than 2, okay? Well, we only define increase and decrease over intervals, so it doesn't matter. Let's suppose it's continuous. So, I mean, there's lots of different options here, but what function can you think of? So this would mean, let's see, what does this mean about the derivative? This means that we want dy dx what? Positive, right? For x less than 2. And what do we want here? We want dy dx negative for x greater than 2, right? Mm-hmm.
It's got to be two different slopes. Well, we just go like this. This is 2, x comes back down, right? So, but what about when x is equal to 2?
I think it has to be, well, I said it's continuous, so yeah. So, but you're right. I mean, you're both right. It could be, well, if it's continuous, then it's a local maximum. In fact, that's the first derivative test. If the function wasn't defined, you could have like a vertical asymptote, yeah. Or you could also have that kind of mismatched behavior. Now, let's see here. So here's a formula that we could do. I mean, you could do lots of different things, but the thing that appears to me is, so, look at this. This is the same as x minus 2 less than 0, right? This is the same as x minus 2 greater than 0, right? So why don't I just do 2 minus x here? Would that work? If x is less than 2, right, then 2 minus x is positive. If x is greater than 2, then 2 minus x is negative. So solutions to this differential equation should follow the geometric data that I gave to us at the start, right? And then you can solve this. How do you solve it? I mean, this is dy dx is what? Well, dy is 2 minus x dx, right? So what do we get? We get y, integrate both sides, right, is equal to 2x minus 1/2 x squared plus a constant, which, we could, it's a parabola. And you can kind of guess what 2 is, right? well, that's not what I want to do. I'm sorry. Actually, I don't want to do anything. The point is it's a parabola, and I think you know what the significance is of 2 just geometrically. I mean, we have enough data here already. If we look at 2, right? This is a parabola which opens down, right? So we're looking at parabolas there. I'm not sure exactly what they, but there's something like this. This is supposed to be a maximum here, right? Now, to get your answer, Josh, what you were seeing, instead of doing this, we would just do dy dx equals to 1 over 2 minus x.
Is it 1 over 0?
Now, as x approaches, as x approaches 2, we get infinity there, so we get a, you know.
That would be ln 2 minus x.
Yeah. Which, what's that? I think so. Well, the thing is, this, what it looks like is minus a log. So minus a natural log, that's going to infinity, because the log goes to minus infinity as we approach 2 from either side. And so it's kind of like a really, and I think so at like 3, well, it depends on which value of c we're looking at, but it's, I believe, it's something like, if c is equal to 0, that's just the one that, c equals 0 is the one that has like 3, 0, and 1, 0 on the graph. That's the c equals 0, 1. Because natural log of 1 is 0, so that's 1 unit to the left or right of 2. Anyway, do you guys see the idea? If you want some geometric data, if you know something you want about your slope, you can set dy dx equal to that, and you can maybe find a family of curves which has that feature. Yeah.
I actually missed why you put dy dx equal to 1 over 2 minus x.
Okay, so I said, what would the curve look like if it had this up here, right? And I said, if it's I said, suppose it's continuous, then this would be it. But then Josh was thinking, well, it could also have like a vertical asymptote, dropping the continuity. If it had like a vertical asymptote, it could also have this increasing from one side, decreasing from the other feature. This was more natural to Josh, and I was just showing that if we could still have the same sign features, like plus and minus from one side or the other. By doing that, we just end up with a, well. Now, depending on how much information I give you, there may or may not be a unique family of curves that, does that. And so I don't really have problems I assign like this. I'm just trying to get you guys to think about a geometric idea. Okay, so let's look at something more. Here's a problem I would actually assign you. So example 3, consider x squared plus y squared equals to r squared. Find family of orthogonal trajectories. What's that mean? Now, this is simple enough that I can draw you a picture of what we're trying to do even before we do the calculus, okay? So what's x squared plus y squared equals to r squared? Yeah, circle radius r, so it's just this thing, right? So what would we mean by orthogonal trajectories? What is an orthogonal trajectory to a given curve? It's another curve which intersects the given curve at a right angle. Yeah? So you call them, if you wanted to, you call them perpendicular trajectories, but then people would think you're crazy because nobody calls them that. But then again, we'd all know what you meant. So anyway, here they are, right? I don't guess we even need calculus really to know that. You can kind of see that they should be concentric lines to the origin, right? But let's use calculus to derive that, all right? So think about it. Let's say, how should dy dx on the circle, how should that be related to, well, let me say it the other way around. Dy dx on the line, how should it be related to dy dx on the circle? They're perpendicular. What are the relation between perpendicular line slope? Yeah. No? Well, I mean, that's what I'm saying is that the tangent line to the circle should be perpendicular, right? Whichever point we're thinking about. So, in other words, what's the relation between the slope of the blue line and the slope of the red line? Yeah, negative reciprocal. So specifically, that means -1 over dy dx for the circle. So if you want to find orthogonal trajectories to a given curve, what you want to do is figure out what's dy dx for your given curve, and then you solve dy dx equals to minus the reciprocal of whatever that is. So what is dy dx for the circle? That wasn't given to us, was it? So we got to figure that out. How do you figure out dy dx for a circle? Yeah. Solving for y. Let's not do that. Yes. I mean, you could do that. It might work out okay, but it would take us down this unpleasant road of square rootedness that would be a detriment on a test or something. So like we can just differentiate the equation. So x squared plus y squared equals to r squared. See, differentiating gives me what? It gives me 2x plus 2y dy dx equals to what? What's the derivative of r squared? Well, it's 0, right? So you see dy dx for the circle is what? It's minus x over y. And then what I want to do is go put that up in here, like that, and solving the differential equation up there should give me the orthogonal trajectories to the circle. So let me just clean it up a little bit. So what we want to do is we want to solve, let's clean it up a little bit, we're interested in solving dy dx equals to what? Minuses cancel, right? We just got ourselves a y over x. So how do we solve such a problem? Well, separate variables, right? So this is going to give us dy over y equals to dx over x. So this time, we got log on both sides, right? We got natural log the absolute value of y equals the natural log the absolute value of x plus some constant. Next move, exponentiate both sides, right? That gives me that the absolute value of y is equal to e to the natural log of the absolute value of x plus a constant, right? Which is equal to e to the c times e to the natural log of the absolute value of x. In other words, we get the absolute value of y is equal to e to the c times the absolute value of x. Which is to say that y is equal to plus or minus e to the c times x.
Can't you have solved for that without even doing all of it?
Hmm?
You have to do all that to find the, because technically wouldn't any line that passes through the origin.
Right. Again, from the start, we don't need calculus to do this problem, but I want to show you how to derive it with calculus because I can change this problem ever so slightly, and then you can't draw the picture. It's as simple as doing this. And to throw a monkey wrench in your plans, I'll do one of these and throw in one of those. Aha! See, now you're in trouble. Now you can't solve for y, and you got to implicitly differentiate and think through it. We'll do that one next. Okay, so therefore, y equals to mx, right? Now, I can throw in m equals to 0 as well, right? Where did we lose that? Back up here, we lost y equals to 0, right? Yeah, we got it back with the formula at the end. If we just let m be 0, which of course is not justified if it's plus or minus e to the c, right? So when I put in 0 as a possibility, I'm going back to the original problem and observing that, hey, if I put y identically 0, it solves this differential equation, okay? Now, some of your homework is written in a different notation, which is called the Pfaffian notation. Like what's Pfaffian notation? Well, Pfaffian notation, show you in a second here. Actually, maybe I could try that one. I'm not sure I should, though. I should? All right. Let me make it a little bit simpler. Suppose we've got x, y cubed plus xy squared equal to, I don't know, e to the x. Wait a minute, that's not better. What am I doing? I'm sorry, let me stop making up problems worse than the ones I've asked you to work. In fact, let me take a moment and actually work one of the problems I've asked you to work. That would be a good idea, right? Or something like it anyway. Nah, it's no good. I'm trying to remember where these pesky orthogonal trajectory problems were. I found them in here. So guys, there are some interesting problems in this book, and I have tried to steer away from them. I've really just given you guys the sort of straight down the middle fastballs, if you will, of this stuff. There's, of course, much more to learn, but I figure you've got a course in differential equations for that. So here we go. This is page 406. This is orthogonal trajectory problems. I'll try to work one of the even ones for you, since I didn't assign those. Let's try to do number 50 of section, where are we? 6.3, I think. So I'm faced with y squared equals to 2cx. I'm supposed to find orthogonal trajectories to this family of curves. Now, what is this family of curves, by the way? Right, sideways opening parabolas. What about when c is equal to 0? C equals 0, I got y squared equals to 0. What's the solution to that? Yeah, I guess just y equal to 0, huh? Huh. That's funny.
What if c is e to l, like any other problem?
I was kind of expecting x equal to 0 as a possible. Huh. Oh, anyway, let me get on with this. So you can plot it, right, if you want. So suppose we want to find the orthogonal trajectories. Well, first of all, we need to find the differential equation. So one way you can do this is to take the differential. Now you guys will learn more about this in Calculus 3. You may or may not have seen this in Calculus 1, but the differential of y is 2y dy, right? And that's equal to 2c dx. Now, so what that gives me, of course, is dy dx equals to what? C over y, right? 2's cancel. Divide by y. Now, I must get rid of that c. How do I do that? So if we look at that, if y squared is 2cx, then what's c? Y squared over 2x? Okay. So this is really y squared over 2x times what? 1 over y, because that's my c. Right, so in other words, what we have here is dy dx is equal to y over 2x. Is this the orthogonal trajectory? No. At the moment, all we've done is found the differential equation which the given family of curves appears as a solution to, right? Okay. Somehow cut the palm of my hand. What on earth did that? Not cool. Anyway. The cookies? It was the cookies? Yeah, I certainly hope not. Now, so to find orthogonal trajectories, we need to solve dy dx equals to what? Minus the reciprocal of the given. So minus 1 over y over 2x. Yeah, which is what you just told me, but I'm just trying to emphasize what I'm doing here. So minus 2x over y. So what is this? This separating variables, we've got y dy equals to minus 2x dx. Now you integrate both sides, what do we get? 1/2 y squared equals to minus x squared plus a constant, right? So therefore, my orthogonal trajectories look like x squared plus y squared over 2 equals to a constant. This is my OTs, your orthogonal trajectories to the given family of curves. Yep.
That's 1/2 y squared because you did implicit differentiation to begin with.
I'm just integrating y dy. The integral of y is 1/2 y squared. Whereas over here there's a 2. So the integral of x is also 1/2 x squared, but that 2 cancels. Okay. Now let me just take a second here to smell the roses, so to speak. So we eliminated c, and the Pfaffian form. So this differential equation could be written in Pfaffian form as follows. In Pfaffian form, this is 2x dy equals to y dx, or better yet, y dx minus 2x dy equals to 0. This is the Pfaffian form. Of the given ODE. Yes. Indeed. Now, what's the Pfaffian form? This one. Well, here you got yourself a y dy equals to minus 2x dx, which of course we can rewrite as 2x dx plus y dy is equal to 0. So can you see any kind of like relation between the Pfaffian forms of the OT versus the given family? They are related, aren't they? So it looks like what we did was we traded the coefficients of the dx and the dy, right? And what else did we do? The two x's switched spots too, but we put a minus on one, right? So if you study this for the given curve, this is the given curve. If you pick a point, this vector, which is actually going to be y comma minus 2x. So this is the given curve. If you study this, in fact, in Calculus 3, we ought to, you can prove that the vector field y comma minus 2x is going to be perpendicular to the curve. So actually, if you look at the coefficients as a vector, the curves that you're finding solutions of, they end up being perpendicular to the vector, which sort of is obviously there. And then, on the other hand, the orthogonal trajectories would run perpendicular to that, right? So these guys would have perpendicular to this would be 2x comma y. That picture is not quite right. I mean, it's a heuristic picture. Don't take it too literally. But the point is, in fact, well, let me shut up. I've said more than I should say here. The point is, to find the orthogonal trajectory, we just take dy dx is equal to minus the reciprocal of the other functions dy dx, and that's how you find it. That's all you need to know, really. Okay? So we got separation of variables, which I've done a bunch at this point. Integrating factor method, we could afford to do more, right? We got this idea of orthogonal trajectories, right? Sometimes we solve initial value problems. The other thing in your homework that I want you to think a little bit about is the idea of direction fields. So that I can't do without a projector. What's a direction field? Actually, they're not direction fields. They're isocline. They're called isoclines. They're these. And here, yeah, sometimes they're called slope fields. What's he call them? Oh, slope field. Okay, great. So slope field. Sometimes they're called isoclines, but also slope fields. Direction fields are like this, except they've got arrows on them. Sorry, you can all see this, right? No? Okay, let me try. Give me a second here. Let me see if I can't find my handy-dandy website here.
Does Desmos do slope fields? I forget.
Will Desmos do slope fields? It's probable that someone has written that into Desmos, but it's not something I would do from scratch because it hurts my head to think about that. Well, that's encouraging to see. My YouTube commenter saying I made a mistake, and he's not complaining about the camera work for a change. It's exciting.
Wait, is this YouTube commenter who I think he is?
I don't think he's anybody around here. I don't think so, because if it's Darius, it'd be really rude in the sense that he'd be calling you guys morons for not knowing how to work a camera. That would be pretty funny. That would be pretty funny if it was Darius, actually. I don't think so, though.
Shouldn't we all make a secret YouTube account and harass your YouTube?
Item 14 on my website says slope field plotter. So let's see if it'll actually work.
He developed a program like this in Calc 1, actually.
Oh, and what for 133 or for in high school?
In high school.
Look here. So if you guys go, this is actually on my website. You know, item 14 under links to websites that do the math for you. Item 14 is what I just went to, which is this. So let's go back to what I started with today, which was what? M. Well, let's put m equal to 2. Go away. Stop spamming me, Windows. All right. So this is a slope field, right? And so what these little dashes represent is just what? That's the slope that a curve which satisfies the differential equation, this f prime, that's kind of a, I'd really rather that he wrote dy dx is equal to f of xy equals to insert blank here. That would be better mathematics. F prime of xy? But then again, I can't complain too much because of the beautiful pictures, right? I'm quibbling that it should really say this, not, see up here? He's got f prime of xy equals that. I don't know what big f prime of xy would even mean. We don't take derivatives of functions of two variables in here, except when we do, like over there. But yeah. So, but we haven't, let's see here. I think, oh no, so that's not how it works. This one, if you move the point around, it'll find the line which solves the differential equation. And of course, what does it do? It lines up with the isoclines, right? Let's see here. Let's try, what else did we do? We solved, what else we solved? We solved 2 minus x, didn't we? So as I said, parabolas, woohoo. Now some of your homework problems basically just ask you to connect the dots. So connecting the dots in an isocline plot, it's a little bit more sophisticated than you learned when you were, that age. It's actually, because the dots have a direction, right? So you got to you connect, if you go through a point close to it, you got to try to make the slope close to the nearest dash, and you just try to, your goal is to not go against the flow, so to speak, In fact, that green line is what you might call an integral curve if I was to put arrows on these. What else did we do? Oh, we did, what was it, 1 over 2 minus x? We're detecting a slight numerical trouble in the GeoGebra code. But I can't complain again. That's pretty nice. Let's see here. What else can we look at? If we do, what should happen if we do x over minus y? Oh.
Are you able to zoom in at all?
That is funny. Wow. This is such an interesting curve. Look at that. That's amazing. See, this is why you should take calculus. Because part of the reason you take calculus is you're supposed to be gaining enough intuition to know that this is not reality. This is the computer messing up. More specifically, this is the programmer failing to anticipate the nuances of hitting vertical tangents in the graph. See, it's got trouble with the vertical tangents. Because the program apparently is thinking of y as a function of x, So it's, here, let me show you something which doesn't suffer this fate. So let's put on our big boy pants and use direction fields instead of slope fields, because direction fields are, well, awesome. And where did that go? All right. Now, what this is for looking at is autonomous systems of differential equations. So you're looking at dx dt equals to fill in the blank, and dy dt equals to fill in the blank. So this is the parametric version of what we're doing. Suppose you're given 2 differential equations, one for your x parametric function and one for your y parametric function. Now, we can game this software by just putting a t here, right? If we put a t, oh, excuse me, just putting a, I'm trying to think here. What do I want to put? I want to put 1? Yeah, if I put 1 here, that makes x equals to t, right? So if I do that, and then I just put f of x comma t down here, that will do the same thing that the GeoGebra app was doing. I'm just kind of, this has the same meaning. It's just going to have arrows in it. I'll show you. So we were just looking at, what was it? Minus x over minus y. Now, this is a direction field because you see little arrows. They show you the direction in which the parametric curves are going. This is one of the built-in things into MATLAB. This is called PPlane. This is, of course, something overlaid on top of that. And it also has trouble at the vertical asymptotes. But you see, not quite as bad, though, right? And the other cool thing about PPlane is that when you click, it puts the solution for you, and it keeps putting more and more and more and more and more and more and more, right? Here, let me see if I can remember. What was that one? Just this one I want to show you guys. Really, really cool. Give me a second. I gotta find it.
What is the equation or equations of the stuff you have in the background? Or is that just evolved by paper that you chose?
Oh, I took a picture of something and ran it through various, you know, what are the words? Curses. That's not what I want. Oh, it's the Fourier sine decomposition of the square wave, like the first 10 terms or something. You can write any function as a sum of sine functions if you want to. And that's a picture of that fuzzified.
Is it section 5.15.2, 5.4? See solutions and play with PPlane?
You'd think that, but no. I'm looking for something very specific. Oh well. I thought I might find it. It looks like I'm not going to. But I don't know, you can go with this and play with, see what happens.
So is that how Pepsi came up with your logo?
So the really neat thing about P-plane, right, is that you can take a differential equation. You notice that I haven't even attempted to find a solution to this thing. And nevertheless, we can actually see the behavior of the differential equation by direct visualization. Sort of qualitative numerical methods is really neat. What's going on here is that differential equation has y prime is 1 over x squared plus y squared minus 2. So something funny happens when x squared plus y squared is equal to 2. There you get like vertical, you get undefined, you get funny points in the curves. So this is that circle, radius root 2, that I made happen there. If I change that to a plus, it'll be very different.
Is there something that drafts these like in 3D?
In 3D, no. Well, see, you know, people always ask that, is there a 3D version of this? I don't know. How do you visualize? I mean, it's troubling to even visualize.
That looks like
Here, let me show you something. So here's calculus 3. My notes? Yes. So like, I do have a table of contents. I guess I could use it. Well, anyway, for example, look at how complicated this is. I mean, here I'm just graphing arrows for some subset of 3 dimensions, right? So the analog of what you're saying would be to put arrows throughout 3-dimensional space and then somehow try to see how lines line up with those arrows. To see that by perspective on a 2-dimensional surface is like, I haven't seen it done well. Anyway, okay, so I think we're pretty much done. So Monday, you guys bring your homework questions. We'll spend the whole day working on the homework with you guys, okay? So.